All right, howdy folks. Welcome back to Professor Carbon on YouTube. Please go ahead and subscribe to us. And what we're going to go over today is actually a bunch of reactions that might be included in standard chapters on either ketones, aldehydes, esters, amides, etc. And so it's generally content for the second half of the second semester of Organic 1. As with all these videos, what I encourage you to do is actually to take a minute and go through and try to work through these problems all on your own before just listening to the answers I'll provide. And for those of you who are looking for access to these problems or the PDFs, you can get those on our Patreon page by becoming a Patreon subscriber / follower. And so why don't I just give you a quick second to try to see if you can add in all these reagent starting materials or products, and then I will go through them here in a second. All right, welcome back. Let me just zoom in on the top one here, and let me see. The starting material here is going to be an ester, so that's going to be our key first clue on this one. The next reagent here is going to be a Grignard reagent, in this case phenyl magnesium chloride, and we're given a clue here for excess. And so if we're going to add this Grignard reagent to the ester, that would generate, as an intermediate here, we can kick off this OME. So remember, a nucleophile coming in will attack, and then we'll kick off the OME leaving group in the second step of that mechanism to do an acyl substitution to generate the aldehyde. Now, one consequence of making an aldehyde is that that aldehyde is going to be several orders of magnitude more electrophilic than the starting material. And so that aldehyde will get very quickly consumed to generate a product such as this. And so that should be the intended product here. Now, some people have asked me, what happens if you use exactly one equivalent of this Grignard reagent and exactly one equivalent of this ester? Or even what happens if you use excess of the ester and you use one equivalent of the Grignard reagent? Is there a way to stop at the aldehyde? And the answer to that, unfortunately, is no. And the reason is because after, if you have this aldehyde and you have some of this ester, and that Grignard gets its opportunity to attack here or to go over here, it's always going to go towards the aldehyde. Aldehydes just fundamentally are that much more reactive than esters, where as soon as you generate a little bit of that aldehyde, it's going to be very rapidly consumed to generate the alcohol product, and you're going to be left with more ester. And so unfortunately, when adding Grignard reagents to esters, it's very difficult to get them to stop after one addition. It'll almost always go to the double addition. And that means that you might have some ester left over and some alcohol product being formed. All right, the next one here, part B. Let's see here. MCPBA is an oxidant, and usually we know about MCPBA for making epoxides. So that is the #1 way that we know about MCPBA. So the fact that it's given here and there aren't any alkenes or double bonds in this molecule other than the carbonyl should give us a clue that something else is amiss. And this, if you're unfamiliar with it, are the conditions for the Baeyer-Villiger oxidation. And the Baeyer-Villiger oxidation is a way to just stick an oxygen directly in that ring. And so what we're going to do is go from a 6-membered ring to a 7-membered ring, if I've drawn that correctly. 1, 2, 3, 4, 5, 6, 7. Yep. So we have a 7-membered ring with an oxygen in there. And so this ring expansion is a very cool way to make 7 or 8-membered rings using the Baeyer-Villiger oxidation. If it's not something that you're familiar with, just do a quick YouTube or Google search for the Baeyer-Villiger oxidation. All right, next one up here, we have a nitrile, and we have to add reagents. And we're going to have a ketone with some spinach dangling off of it here in the product. And let's see here, we know that we can add organometallic reagents to nitriles. And so a very good common answer might be magnesium bromide. Remember, the halogen here is really irrelevant when drawing out these reagents. So we could also imagine the magnesium chloride or the magnesium iodide. And for those of you that would like, you can also imagine vinyl lithium, although realistically we would probably use the Grignard reagent in the lab. And then after that Grignard reagent, we want to have then some H+ workup. because the intermediate that you get, remember, is the N anion. So we would add our vinyl piece here, and then we'd have N minus, and we need to be able to hydrolyze this piece off to get to the ketone. And so it turns out that's going to be an important part of this reaction. All right, next one up here is a amide. That's our key functional group here, and it looks like we have an amine, and so what we have to do is come up with a way to get rid of that carbonyl oxygen. So removing oxygen would be a reduction. So for certain, we're going to need some kind of reducing power. And amides are our most stable functional group, and so we're going to need a really powerful reducing agent to complement or to partner with that really stable functional group. And so I would recommend lithium aluminum hydride, which for those of you that have been following this channel, you'll know I identify as our big sledgehammer reducing agent. And the reason I say that is it knocks the oxidation state of almost everything down. All right, and so LAH is a very powerful reducing agent. Now, some of you might be tempted to put then HCl wash in here. For that, I actually would be a little bit concerned because remember this nitrogen here is basic. And because it's a basic product, if we protonate it with something like HCl, we might actually pull it into the aqueous layer, and we might not be able, or might have some problems isolating it. So I would probably actually just leave it as HCl. And if we really want to highlight a workup, I might say then water is our workup. But I would probably avoid HCl on this one because you would protonate the amine product, and then you'd have to re-back extract it. All right, two more here on the list. Let me see. This one is a little bit more complicated than what we're used to. So let's look at this. What is thionyl chloride used for? One thing that it's used for is to take a carboxylic acid and make it into an acid chloride. So that would be good. And then let's see here. This is our second. So that's an amine. So that would be a nucleophile that would partner with that acid chloride. And if I look over here, that phenyl, now I have two phenols to choose from. So there's a little bit of difficulty there, but there's a CH2N. And so I can see a CH2N there. So this whole piece is this piece. And then that would mean that if I chopped this molecule right here and took it back to an acid, I would be able to convert that acid to the acid chloride with the thionyl chloride, and then we could make the amide in the second step. So let's go ahead and draw that out. And so I would put that down as my answer. All right, the next step here, this is kind of an unusual reagent, and it's actually pretty atypical that we see it fully drawn out like this. And so there's a little bit of detective work to figure out what on earth is this reagent. Now it has an aluminum hydride in it, so just like our lithium aluminum hydride, that should send off some bells that we're going to do some kind of reduction. And we do have a nice high oxidation state nitrile here. And for those of you that might have forgotten, this is diabol. Sometimes it's written as diabol H, and it's a special version of lithium aluminum hydride that has some really nice properties. And one of those is reducing nitriles to their aldehyde oxidation state. And it's actually typically a very clean reaction, and it stops at the mono addition because the intermediate is that C double bond N with an H and an R coming off of it. And so because of this adduct, it again is kind of stuck there. It's not willing to accept an N-2 oxidation state, and it kind of sits around until we work it up. And so if we wanted to actually be fully technically correct here, we might put then an HCl. But sometimes we leave that workup off for these kinds of problems. All right, so that is a number of reactions here that you might be able to pull out of a chapter on carboxylic acids and lactones, or amides and nitriles. So for those of you that are enjoying these videos, please do subscribe to the YouTube channel. That gives us a little bit of encouragement to continue making these videos. Also, please do feel free to subscribe to the Patreon page if you want access to the PDFs, both before and after they're filled out. Please tell a friend, please share, and please like us on social media. Thank you.